In this first problem, we're revolving this first quadrant region between an exponential function and a horizontal line about the y-axis. So as soon as you hear that we're revolving about the y-axis, you should realize that we're going to have to use horizontal rectangles. So our disk will be horizontal. So we're going to have these disks going from this point here at the bottom, which is clearly at 1, up to 4. So we're going to come up with an integral that's moving vertically, and our independent variable has to be the y variable. So we're going to need to find this intersection point here. We can do that with our calculator, and we're also going to need to reverse our function. So if I want to get a variable out of an exponent, I'm going to take the natural log of each side, and then the log of a power becomes the power times the log, and of course many times we've decided we don't need to write that. That will be a 1. So when we write this function with y as our independent variable, that tells us how we can find the coordinate of each point. So this point here at the center, if we use y generically as our point, this would be the point 0y. That's a little too small for you to read, isn't it? I just wrote 0, comma y. So this point over here would have the same y coordinate, and now we know that its x coordinate would be the natural log of y divided by 0.9. So this distance between these 2 points tells us the radius of each of our disks. So we're almost there already. As long as I've done that, let's put a typical disk in here. There's pi. Our radius goes from 0 over to this value. So we want to square that. So there's our typical disk, a pi r squared, from 0 to 4. So this intersection point, when we're moving vertically, do we care what the x coordinate is? We only needed to find the y coordinate. So you don't jump the gun looking for your intersection point until you know whether you care about the x or the y coordinate. And since we've got this horizontal line, we already knew our y coordinate goes up to 4. So you could enter this in your calculator. So let me find my graphing calculator, and I'm going to pause while I put that function in so I don't use up your video time. I'll be right back. All right, as I was putting that in my calculator, I realized I wrote here on the tablet a lower limit of 0, but of course we have a lower limit here at 1 up to 4. So back to the calculator. A suggestion I would make is always look at the pretty print after you put in a function, and I use the variable y since that's what I had written on the equation, but you could certainly, out of habit, always use the variable x. And green diamond enter would be another suggestion to make sure your calculator, if it has a decimal in the calculation, is going to give you a decimal value. But if there are no decimals, then remember green diamond enter will be your shortcut way to make sure you get the approximate answer from your calculator. So I should write down 10.072 if I'm reading that correctly. 10.072. All right, let's try another here. We are now using this region R. So between, let me get a highlighter, the region between this horizontal line and this function, this polynomial function. So we would like to first find the volume if we revolve this region R about the horizontal line y equals 3. So it's going to be 1 unit above and some sort of mirror image here. Just do the best you can to make something that looks like a mirror image, and then we're going to have a typical Riemann rectangle is going to revolve up here. And let me first just draw the inner radius so we can talk about that. The inner radius goes from this point, which would be at some x coordinate, to a y coordinate of 3, to this point, which is at the same x coordinate with a y coordinate of 2. So our inner radius is the distance between those two, and it's going to be 3 minus 2 all the way across. So of course you could just write 1 for the inner radius of the circle as we move across. The inner radius right here is the inner radius, so it is going to have a length of 1. All right, now let me switch colors here and finish drawing our washer. So here's our washer to the outer function. So from this point here at x comma 3, we are going down to this point right here, which we'll call x, and to keep it simple, let's just use f of x. So our outer radius goes between those two blue points. So our outer radius goes from 3 on top down to f of x, the y coordinate on our function. So as those washers sweep across, and they are going to sweep across from 0 over to this intersection point. So we're going to have to find out where does our function intersect the line. Again, this is our line y equals 2. So we're going to put both of these equations, f of x, into our calculator, and the horizontal line, we just put y is equal to the constant of 2. So again, let me grab the calculator and enter those in my y editor for you first. All right, so change your window so you have a nice view of this region. And we know this intersection point is at 2. You can see the y-intercept of this graph is at 2, and our line y equals 2. So let me erase some of my notation here and go back to the calculator. So what we need to find then is our intersection point. We know this point is at 0, 2. So we need to find this intersection point. So we'll go to F5 and choose 5 for intersection. And we only have 2 graphs here. So is function 1 my first curve? Yes, I'll hit enter. Is function 2 the second? Yes, I'll hit enter. And then I want to move to a lower bound to the left side. Hit enter. And I'll move the cursor to the right side of the intersection and hit enter. And then we're going to make a note of this 1.7 and transfer these digits. So I will move this intersection point, and my window, as soon as I start writing, I'm going to lose the calculator. So I'll pause while I transfer this also. So you might not choose to write it this way, but here to save myself some time in part B, where I'm going to use A again. So I'm going to say that I'm going to use the letter A to represent the x coordinate of the intersection. So make some sort of notation. On your AP exam, you can't just write that on the graph, because the graph might not be part of your solution rectangle. All right, so now we've got everything we need here. So remember we've got these washers with our pi r outer squared minus pi r inner squared. And we know that the washers are moving across from 0 to A. So that's the advantage of writing it down just once. And then we could bring our pi to the outside if you wish. Then all we have to do for our washer method is our outer squared, and it's easier than rewriting that function would just be to put f of x. It's already named on your paper, so f of x is not ambiguous. And our inner radius, remember, was our 3 minus 2. So you could either write it as 3 minus 2 if you wish to be very specific, but of course if you just wrote the number 1, that would be just fine as well. And then a dx. And this one we have to come up with an answer. So Again, let me pause to put this into the home screen of my calculator and get an answer. And again, make sure when you calculate that you go check your pretty print to make sure that you have things entered. Now, I didn't need this many digits, by the way, in that upper limit, but do not use only 3. Make sure in the middle of the problem that you use more than 3 characters. And then notice here for the inner radius of 1, this really represents 1 squared, so that would be fine if you wrote that on your paper. So we've got an answer here of 11.13, and then if you're going to do only 3 decimal places, make sure you round to 2. Otherwise, 11.1318. If you don't round, you can always give more than 3 decimal places. And we don't know the units, so we need not label them. You could put units cubed if you wish. And notice that I put an approximately equal sign there. That would be another good habit to stay into. All right, let's move on. So here we want to practice differential equations. The rate of change with respect to time of a population. The change in population with respect to time is proportional to the current size of the population. So I hope this looks familiar. There's our differential equation. And now we want to come up with a function to represent it. So you very well might remember that that direct proportionality led us to this model. And if you remember that, you can just go right to that step. Let's say you did not remember that model. Then you'd have to do separation of variables. So let's take our previous statement and let's divide by p and multiply by dt to separate the variables, and then integrate. So we had the natural log of the absolute value, and now you can quickly get rid of this absolute value if you say that the population is never going to be negative. So in these problems, that absolute value is not so essential. Don't forget your constant of integration. And now the question here, so if we say p is always greater than 0, then in our next step we can drop the absolute value signs. The question is, when do you want to find the value of the constant? But remember that in these problems, that constant is going to turn into our initial population. So let's exponentiate each side. So e to the ln of p becomes p, and e to the kt plus this constant, remember, is our e to the kt times e to the c, and that c1, that e to the c1 became our constant. So that's where we came up with our model. And then remember, when time is equal to 0, let me scroll here. When time is equal to 0, this is where we're putting in our initial value, which I scrolled a little too far. Our initial value was 50. So we know that the population was 50 when t is equal to 0. And e to the 0 power is 1. So that was how we knew that our 50, the initial population, could immediately be written in here for c. So if you remember our exponential functions, it saves you some time. But if you're not sure that you've got it memorized, then of course better safe than sorry. Differentiate or integrate rather to come up with that. All right, remember then k was called the relative growth rate. So we have to find the relative growth rate by using the next data point. So we know the population is 150 when t is equal to 5. So then we can find out what k is. So we divide both sides by 50. And then to get our k out of the exponent, we take the natural log of both sides. The log of a power becomes the power of a log. And of course, we don't need this natural log of e is, of course, 1. So our k value is 1/5 the natural log of 3. So now we've got a function for our population at any time. So we could write this as t over 5 ln of 3. And then remember that there was one optional way of writing that. Let's look again at this value to remind you. You do not have to do this, but remember you should recognize that if you did this order of operations differently, so if you wrote it this way as a power of a power, then e to the natural log of 3 is just 3. So our alternate version, and you should recognize both, either one of them is acceptable, but this becomes 3, and then we would just have our t to the 5th. So you may calculate the next part of the problem using that version if you prefer. Our last part of this problem is, when will the population reach 200,000? Well, be careful about this. We're really just setting our population to 200 because remember in the problem it talked about the population in thousands. So we want to just set this to 200 and then solve for the variable t. So we might as well pick this one as long as I just wrote it. Divide both sides by 50 to simplify first. And to solve when the variable is in the exponent, that's why we need logarithms. Take the log of both sides and bring the power down in front. So we can solve for t, multiply both sides by 5, divide both sides by ln of 3. And if you put years, you are done. If you prefer to have a value, you could round that off. And I will do that, calculate that, and be right back. When you're calculating with natural logs, don't forget the order of operations there to close your parentheses so you save some time. And if I just hit enter, there's an example where you see that it's giving me the exact answer. So here's where you'll have to use green diamond enter if you want to round. So it looks like we have 6.3092. So we'll do 6.309 years. All right, so either of those, the exact value or to at least 3 decimal places. And then we have to do a differential equation. We have to do a slope field, a very simple formula here. Important to notice first thing, y in the denominator. So y cannot be 0, so notice that there's no slopes on the x-axis. If x is -1, that's the easiest pattern I see, because if x is -1, the numerator will be 0, so I can put horizontal tangent lines there. And then let's just start thinking what we would come up with here. If we have x is 0 and y is 1, we get a slope of 1. If x is 0 and y is 2, we get a slope of 1/2. At 1, 1, we get a slope of 2. And you can tell I'm not being very careful here to move quickly. And when x is 1 and y is 2, we'll get a slope of 1 again. And what do we have left here? At 0 for x and a -1 for y, we'll get a slope of -1. 0 for x and -2, we'll get a slope of -1/2. At +1 for x, our numerator will be 2, but our denominator will be -1, so a slope of -2. And when x is 1 and y is -2, we'll get a slope of -1. All right, so is that enough that we could actually see a pattern of what might happen here? So curves that might be going this way, and of course that is, we don't know, we can't necessarily go off of our slope field, but you can kind of see what's going to happen. And most importantly, remember that y cannot ever be equal to 0. So our solution curves will either have to be completely above or completely below. So we are asked to draw one solution curve through the point 0, -1. So difficult to to see if it was anywhere else here, but here we had these slopes of -1. So what happens here? We have to hit our barrier. So we have to do an empty circle there because y cannot be equal to 0. All right, so for part, this is Microsoft relabeling A, B, C. All right, for part B, while the slope field is only drawn at 12 points, it's defined everywhere except at y equals 0 is not defined. So can we find the points where the derivative would be equal to 1? Sounds complicated, but it's just substitution. We want the derivative, so take your derivative formula. And all we're asked to do here is to find out when is that slope going to be equal to 1. So it's really just a simple proportion. Let's multiply by y. And then we would like this to be a function, so let's do the opposite of each of those. So this line would describe all the ordered pairs. We could be more specific. This was in algebra called set builder notation. So it's the set of all of the points x, y on this line. And you could write that in words if you've forgotten how to write this in symbols. You could say it would be all of the points on the line, -x minus 1. All right, part C, now we have to solve our differential equation. So notice our derivative has x's and y's mixed. So here's our separation of variables again. So I'll move the y with the dy, and I'll multiply the dx to the right-hand side, and then we'll integrate. We've got a power rule, raise the exponent and divide. Here we'll have a power rule on the x, raise the exponent and divide by it. Raise the exponent, this would be x to the 0, but we know this term will just become an x to the first. And then we'll lump our two constants together. You could right away multiply everything by 2 if you wish, or you could do that later. So I'll do that right away just to show you that then what I would do is change from constant 1 to constant 2. And you might have noticed some papers where they actually would say where C2 is equal to 2 times C1. But I don't think you'd lose any points if you did or did not do that. We need at some point, we're going to take the square root, but we need to find the value of C. So let's find our initial value, which I've forgotten. Here it is. 0, -2 is our initial value. So we'll have, when we put -2 in for y, and we put 0 in for x, we will see that our constant is just equal to 4. So now we have only one step left to do, and that's because we're going to take the square roots. If this were algebra, we'd have both plus and minus, but don't you dare leave a plus and a minus. That would fail the vertical line test. So remember our slope field? We talked about our slope field could have curves up above and curves down below. So you couldn't have 2 of those curves because that would not be a function. So we have to pick one, and we choose one by looking at our initial point. So we would say since 0, -2 is a solution, we are going to have y is equal to the negative square root of x squared plus 2x plus 4. So you didn't need to write this step at all. You could go right to that conclusion. And I think that does it for us.